For the last 2 months, me and my team have been working on an implementation of the Martian tetrahedra algorithm. This talk will begin with an explanation of what the algorithm achieves, followed by an explanation of how it works. The Martian tetrahedra algorithm is a method of creating isosurfaces from a scalar field. An isosurface can be thought of as a 3-dimensional equivalent to a 2-dimensional contour. More formally, it is a closed surface that represents a set of points of a specific isovalue in a scalar field. For example, the isosurface for an electric potential of a point charge is a sphere with a radius inversely proportional to the chosen isovalue. Isosurfaces are used to visualize scalar fields, such as those encountered in CFD applications or medical imaging, but in our case, we'll be using it to view the electron densities of a complex protein. Our program has 3 main stages. First, we calculate the electron density of the protein using the Slater approximation. Secondly, we extract a mesh from this field using the Martian tetrahedra algorithm. And finally, we simplify the mesh via vertex and edge reduction techniques.
For the field creation, we have created a volumetric dataset for the representation of the biomolecular surface. A cubic grid was set up and the origin of the cube is computed, and then the approximate electron density was computed from Slater functions. This was performed for all the atoms, where its nucleus is located at a distance of r away from the point. Then we have implemented a function map2grid to get the results of the Slater density mapping.
The first stage of the Martian tetrahedra algorithm is to decompose a scalar field into a honeycomb of tetrahedra. A simple way to do this is to divide the domain up into individual cubes. Then for each cube, divide the space into 6 tetrahedra. For each tetrahedra, a small surface is then extracted. The shape of the surface extracted is dependent upon the number of tetrahedra's vertices with electron densities higher than the isovalue. Vertices with electron densities higher than the isovalue should be enclosed by the isosurface. Either 0, 1, 2, 3, or 4 of a tetrahedra's vertices can be enclosed, resulting in 5 possible cases. 2 of these cases are trivial. If all of the vertices are greater than the isovalue, then there are no surfaces to extract, and if all of the vertices are less than the isovalue, there is no surface to extract. In the first non-trivial case, a single vertex is greater than the isovalue, which is shown in red in the diagram below. In this case, a single triangular surface is extracted that separates the enclosed vertex from the 3 unenclosed vertices. In the second case, 2 vertices are greater than the isovalue. This results in 2 triangular surfaces forming a quad to separate the 2 enclosed vertices from the 2 unenclosed vertices. In the final case, there are 3 vertices that are greater than the isovalue, and similarly to the first case, a single triangular surface can be extracted. To create the final mesh, individual surfaces are extracted from all tetrahedra in the honeycomb. These individual surfaces are then stitched together to form a single closed surface.
Once the isosurface has been extracted, we perform a so-called mesh reduction. The aim of the procedure is to simplify the surface by removing the small and very elongated triangles that result from the extraction. This yields a more homogeneous mesh. We do this because in the final applications that use it, less triangles also mean less equations to solve. Furthermore, the simplified surface requires less memory and it is faster to be processed. The reduction procedure is quite simple. We identify edges that should be removed and contract them into a single point. The triangles involved are then removed from the surface. But let's see some examples. On the left, we have the original surface, while on the right, the reduced one. It is easy to see that the procedure removed many of the redundant triangles. Here we can see more in detail how the reduction works.
Coming to the geometrical properties of isosurface, there are 2 important properties. First one is the orientation of the triangle. The second one is to check whether the surface is open or closed. The orientation of a face of a triangle is the cyclic order of its incident vertices. There are 2 possible orientations of each face, clockwise and counterclockwise. We have analyzed the orientation of triangle in our mesh and results came out to be that the orientation was not same for all triangles. We have corrected the orientation based on the individual triangles cross product. The sign of the acute angle is the sign of the expression. If the result is 0, the points are collinear. If it is positive, the 3 points constitutes a positive angle of rotation, otherwise a negative angle. The second important property of mesh is to check whether the surface is open or a closed surface. Later, we found that Euler characteristics can be applied for any geometrical shape. It is commonly denoted by chi. Topology is frequently called rubber geometry because in it we are allowed to stretch objects and that doesn't change the topology. Any sort of deformation is also allowed. If two objects are topologically the same, they have the same Euler characteristics. What we are not allowed to do is glue things together. We are also not allowed to tear things, otherwise its topology changes. A coffee cup and a donut are topologically equivalent. To apply Euler characteristic, it was necessary for us to determine unique edges and unique vertices from complete mesh, which needs to be calculated only once. Here, there are two triangles which has a common edge. To validate our idea of using Euler characteristic, we first took a known structure of C60, whose shape was given to be sphere. On later investigation, we found that C60 surface comprises of multiple surfaces. Then we separately analyzed outer and inner surface atom and found that Euler characteristic was true for each case. In the edge-based decomposition, large proportion of small triangles were removed. We identified the total execution time was 44.8 seconds. Then we identified that our function Slater density, which was calculating the density, was taking the maximum time. It was repeatedly called for each atom. Then we optimized our loops and other subroutines and we could reach up to 18.1 seconds. The execution time was further decreased by porting subtasks on GPU using CUDA. Hence, the performance of the algorithm was improved. Last but not the least, I would like to thank our mentors for their guidance and support and praise for giving this opportunity.